Hello everyone, this is Susmel from the University of Sheffield, and this presentation is about the use of the critical distance method to estimate the fatigue strength of notched additively manufactured titanium. This work was done in collaboration with my former PhD student Ibrahim Al-Zamzami, as well as in collaboration with Javed Razavi and Filippo Berto from NTNU in Norway. Present work then is to investigate whether the classic theory of critical distances can be used also to perform the fatigue assessment of notch components of 3D printed titanium alloys when the 3D printed material is used in the as manufactured condition. One of the most important features of 3D printing is that we can manufacture components having very complex geometries, but these complex geometries, from a structural integrity point of view, result in localized stress concentration phenomena. And as we know, stress concentrators are a big problem because they reduce the overall strength of engineering components. In this context, then we need a powerful tool, but at the same time simple, which can be used to perform the fatigue assessment of 3D printed materials, not only in a very accurate way, but also in a very simple way. In this setting, then, the obvious question is, can we use the TCD, the theory of critical distances, to perform the fatigue assessment of 3D printed materials, and in particular the fatigue assessment of notched components made of 3D printed titanium alloys? In the present investigation, we used a EOS M280 3D printer to manufacture the specimens that were tested under fatigue loading. This 3D printer had a maximum laser power of 400 watts, and the specimens were manufactured by using the direct metal laser sintering technology. The parent material we employed to manufacture the samples was Ti6A14V, and the manufacturing parameters were quite standard, and they are shown on the slide. By using this technological process, we manufactured a large number of specimens by considering 4 different geometries. Clearly, we started by testing the plane specimens, having a net stress concentration factor equal to 1. But we also considered 3 different notches, that is a sharp notch having a stress concentration factor referred to the next section equal to 3.37, intermediate notch having KT equal to 2.86, and the blunt notch having KT equal to 2.10 millimeters. The geometries of the specimens are shown in these pictures, and the thickness, the average value of the thickness for all the slides, was equal to 2.7 millimeters. To characterize the mechanical behavior of this material, initially we ran a few standard static tests, and basically the tests were run under a displacement rate of 2 millimeters per minute, and the value of the UTS that was determined for these materials was around 1400 megapascal. That is the same order of magnitude as the one characterizing the static strength of conventional titanium alloys. So, in terms of static strength, the 3D printing process being used allowed us to obtain a material having mechanical static properties similar to the ones that are shown by conventional titanium alloys. The fatigue testing instead was performed under axial loading. The test frequency was set equal to 10 Hz. The failure criterion, since the specimens were very small, was the complete breakage of the sample. And we investigated 2 different values of the load ratio, that is a load ratio equal to minus 1, as well as a load ratio equal to 0.1, where in the first case clearly the load history that was applied was a fully reversed axial load history, and in the second case instead the applied constant amplitude load history resulted in a mean stress larger than 0. The fatigue results generated under fully reversed loading are shown in these SN curves. In particular, these SN curves plot the amplitude of the stress referred to the net area versus the number of cycles to failure. Clearly, for the plane specimens, the net stress corresponds to the gross stress. And as you can see, in the end we obtained the usual behavior that is shown by metallic materials, conventional metallic materials, when they are subjected to fatigue loadings. And the same applies to the results generated under a load ratio equal to 0.1. Here in these 4 diagrams, you can see the results we obtain by in the presence of non-zero mean stresses. Again, the general trend that is observed is very similar to the one which is shown by conventional materials in the presence of non-zero mean stresses. In this slide, you can see some examples of the cracking behavior that was observed in the broken samples. Actually, to be honest with you, it's very difficult to say something definitive about the crack initiation process as well as the crack propagation process. In any case, it was evident that in general the cracks initiate in the vicinity of the notch tip, and the crack initiation process was favored by the presence of local manufacturing defects. All the results being generated were then reanalyzed under the hypothesis of a log normal distribution of the number of cycles to failure for each stress level, and that was done by setting the confidence level invariably equal to 95%. By using this standard post-processing procedure, we managed then to calculate the inverse slope of any fatigue curve being generated, as well as the corresponding endurance limit extrapolated at 2 million cycles to failure. In the table, you can see the endurance limit determined for a probability of survival equal to 50%. But actually, we also calculated the endurance limit for a probability of survival equal to 10% as well as equal to 19%. And the ratio between these two fatigue limits, that is index T sigma, was used to assess the level of scattering characterizing any data set. As you can see from this table, in the end, the negative inverse slope was, the value of the negative inverse slope was quite consistent, and actually the value characterizing the plane curves was very similar to the value of the negative inverse slope characterizing the curves determined by testing notched specimens. As far as the endurance limits are concerned, it's interesting to observe that independently of the geometry, or in the end, the endurance limit determined under a load ratio equal to 0.1 was always seen to be slightly larger than the corresponding value determined under fully reversed loading. And finally, in terms of data scattering, the T sigma values reported here show that, overall the data were quite scattered, and that was basically mainly due to the presence of the manufacturing defects. Don't forget that we tested this material in the as manufactured condition, that is not post-manufacturing treatment was used in order to increase the overall strength of the material being investigated. There was just one series, which is the one with a notch root radius equal to 0.7 millimeters and generated under fully reverse loading, that gave to us quite dodgy results. As you can see, the negative inverse slope is very low, the associated endurance limit is very low, and the scatter band is very, very large. We think that this is simply due to the manufacturing process for this specific batch, resulting in the presence of a lot of defects inside the material. In order to assess the overall fatigue behavior of the investigated material, initially it's interesting to consider this classic diagram which plots the endurance limit versus the ultimate tensile strength, where this diagram was built by considering a large number of different metallic materials, where these metallic materials were manufactured by using standard technological processes. And actually there is this kind of standard behavior where, in up to around 1400 megapascal in terms of UTS, the ratio between the endurance limit and the UTS itself is equal to about 0.5. However, if we plot in this graph the endurance limit, the fully reversed endurance limit we generated by testing our material, as you can see, the point is well below the general trend that is observed when it comes to conventional metallic materials. And this means that overall, the 3D printed technology being used, it allowed us to get a very good mechanical behavior from a static strength point of view, but in terms of fatigue strength, clearly the presence of the manufacturing defects resulted in a very low value for the endurance limit. This diagram shows the situation for the plain material, but actually it was basically the same no matter the sharpness of the notch being considered. And another important aspect is that, this is the classic Goodman's straight line linking the endurance limit with the mean stress, basically, and in general, with the conventional materials, fatigue strength decreases as the mean stress increases. But actually, for the 3D printed titanium alloy being considered here, nothing really can be said. And in fact, actually, it seems that the presence of a non-zero mean stress had a kind of beneficial effect on the overall fatigue strength of the material itself. Having generated the fatigue results we need, and now we can try to answer our key question, that is, can we use the TCD to assess the fatigue strength of additively manufactured notched components of the titanium alloy being considered in this investigation? The theory of critical distances, as employed in the present investigation, make use of two reference quantities, that is the effective stress and a material characteristic length L. Effective stress can be calculated in different ways, and certainly the simplest formalization of the TCD is the point method. In particular, according to the point method, the effective stress is calculated at a certain distance from the notch tip, where this distance is taken equal to L divided by 2. But the effective stress can be also calculated by averaging the stress over a line, where the length of the integration domain is equal to 2 times L, and this formalization of the TCD is known as the line method. Or finally, the effective stress can be also calculated by averaging the stress over a semicircular area centered at the notch tip, where the semicircular area has a radius equal to L. In order to apply the TCD to estimate the fatigue strength of the titanium alloy being investigated, the material was modeled by using a simple linear elastic constitutive law. And in particular, the relevant local stress fields in the vicinity of the stress concentrators under investigation were determined by using FE code ANSYS, and these stress fields were determined by solving very simple bidimensional models. In order to determine the critical distance, then these stress fields were post-processed in a very simple way. That is, for any stress level, the critical distance was calculated according to the point method by finding that point where the stress from the stress distance curve equals the corresponding strengths characterizing the unnotched material behavior. So this distance then, according to the point method, was assumed to be equal to L divided by 2. By so doing, we could determine the critical distance value L for different stress levels, that is, for different numbers of cycles to failure. By using the results generated by testing the plane samples, as well as the results generated by testing the sharply notched specimens, then this simple procedure based on the point method allowed us to calculate the critical distance value as the number of cycles to failure increases. As you can see here from the diagram, basically the critical distance value was calculated both under a load ratio equal to -1 and under a load ratio equal to 0.1. I would say that according to this graph, the variation between in terms of L is very limited as the number of cycles to failure increases. Accordingly, we simply averaged the values we obtained by determining a critical length, a reference critical length for the material under investigation equal to 0.6 millimeters. This constant value for L was then used to apply the TCD in the form of the point method, line method, and area method. The accuracy we obtained by applying both the point method and the line method to estimate the results we generated is shown in these two error diagrams. In particular, the x-axis is the estimated number of cycles to failure, whereas the vertical axis is the experimental number of cycles to failure. So according to these two charts, the TCD applied both in the form of the point method and the line method allowed us to obtain estimates falling within the two scatter bands associated with the two curves used to calibrate the approach itself. And actually the same applies also to the estimates that were obtained by applying the TCD in the form of the area method. Certainly we can say that the obtained results are satisfactory because we cannot ask a predictive method to be more accurate from a statistical point of view than the experimental information used to calibrate the method itself. To conclude, we can initially observe that the cracking behavior under fatigue loading of the 3D printed titanium alloy be investigated was characterized by two main variables, that is the local material microstructural features and the presence of manufacturing defects and voids. In terms of strength, it's interesting to observe that the ratio between the endurance limit and the material static strength characterizing the material we tested was much lower than the corresponding ratio associated with those metallic materials that are used by employing conventional manufacturing processes. This means that from a fatigue point of view, the use of 3D printed results in titanium alloys characterized by a very low fatigue strength. At least this is true if the materials are used directly in the as manufactured condition. In this context, nothing can be said about the effect of non-zero mean stresses. In particular, what we observe is that in the presence of non-zero mean stresses larger than zero, actually, the overall fatigue strength was seen to slightly increase, so which is very different from what is observed in conventional materials. And lastly, the most important conclusion is that the classic TCD is, in any case, seen to be successful also in estimating the fatigue strength of additively manufactured titanium alloys when these alloys are used in the as manufactured condition. Thank you very much for your attention.